Trước khi bắt đầu thì có hai cái là mình muốn nói. Thứ nhất là đây là khóa học high tech, cho nên là bọn này muốn dùng rất là high tech công nghệ, sẽ dùng phấn đen, phấn trắng và phấn đen và set up okay, so let me start the course by giving you really try to motivate everyone. Why should we learn digital signal processing? Right? So just very short introduction and overview of the field, right? Of the field DSP. Okay. So before we understand what is DSP, let's try to understand what does each word mean, right? So we start by signal. Signal really means any physical entity that carry information, right? So anything you see outside there in the real world that carry information, like what I'm talking right now, carrying that signal, the speech, getting to the ear, that is a signal, right? The weather temperature is another type of signal. The video trying to recording me now is another type of signal. So you can see the signal is everywhere, right? Processing is quite obvious, right? It is simply a series of steps that try to accomplish a particular end, like a purpose, like what my mind is doing right now, trying to capture this image signal, and my brain is really processing and trying to really recognize the people in this group. Okay, so signal processing is everywhere. Our brain, our systems, our society doing signal processing all the time. Okay, so you can see the impact of that field. Now digital, what digital means, it is simply mean that signal processing is done by a computer, simply put, right? Because digital is thing that can be done by a logic circuit. So digital signal processing is an area that we use computer to do the processing of the signal, which is everywhere around us. Okay, so everyone understand that? Okay, wonderful. Okay, we move on. So I'd like to put an example here of speech recognition. Something, us, even a child can do it easily, right? You tell them to try something and see or he can, understand it. And we use speech recognition every time to acquire our information and carry our daily life. So how about the speech recognition done by a computer? So it would say something and that going to give you some signal for you to process. You can record it by a microphone, right? There's a microphone with a camera, and that signal, typically the electrical signal, get converted into a digital form, right? The computer, the only thing it can carry is the digital, right? Signal in the digital form, and we will talk more about that. And then there's a whole processing here, which there's a lot of mathematical algorithms, a lot of techniques, right? A lot of computer algorithms running inside that, and do what our brain would do effortlessly, right? All the time, and turn out what is that information is carrying. Okay, so that is an example of digital signal processing put in place. Okay, so everyone understand that? Okay, good. So let me put another example, and this one would be taught intensively later on in the third course, namely compression. Compression is a multi-billion-dollar industry in the US. It's multi-billion dollars, very, very big industry in the US. Think about it. The internet wouldn't be able to be around this day without compression. Why? I have an image, I capture an image, and I talk more about that later. But typically, it's about, the typical image called 3 megabyte of data. Okay, 3 megabyte data, huge. And any of you here have experience downloading, web page on the internet? Raise your hands. All right. I should see everyone raise their hands, right? Okay. It would take forever. And we wouldn't be able to see all the image, and the web page. Now with the compression technology, we can bring that file from 3 megabyte to about 19 kilobyte. About almost 200 times compressed. So instead of spending 200 seconds, right, so 3 minutes, you can see the image within a second. So you see that the internet really the DSP and this, and we talk more about that, and that's a whole course will be devoted to that. To show that how can I take this information and I do digital signal processing, get it to some file in a very small form, and then transmit very quickly through the internet, and download and display the outcome. Yes, you have questions? Okay, using something very latest development. Normally now you have on the internet jailbreak, but the new technology called jailbreak 2000 based on wavelengths. So that is the theme of the second course. I can see the big improvement. The same amount of file that has different image quality here, and there will be a whole course showing you what is amazing behind this. Okay. Let me show you another example of digital signal processing in place. So, anyone here have a digital camera? Raise your hand. Okay, a few people. Who used the old camera before? Okay, a few. Okay, so you are pretty young generation, right? We use, if you remember, you have those old cameras, the film camera, very, very big. And the major emphasis is on the physical property of the camera. Right? You have a very good lens trying to capture the information. Now, the digital camera appeared in the market about 5 or 10 years ago. And really, people put a lot of effort into the DSP, right? The new mathematical algorithms, the new computer algorithms, the new signal processing techniques that really can convert some image you take that has some problems like this or that, right? You see a lot of those. For example, you take an image, there's a black line. Then we can do some very simple signal processing and can turn an image into a very much better quality. So you can see that we use computer power, right, computational power to improve the quality of a physical system. Okay. Everyone understand that point? Right? So that will be the major theme of this DSP, and we come up to it later more and more. Another example that is great, but I want to show you the cutting edge resource now on this. So, anyone have one of these cell phones that have a camera on it? Right? How do you have it? And you know that the cell phone people want to make it really small, right? Very, very small. And you want to put a lens there, and the lens is very small, right? You cannot make a very big lens. So the image you have nowadays from one of these cell phones are very poor quality, and nothing you can do about that in the physical side, right? Because the camera is very small. So the thing people now try to do, they put a lot of DSP power here. There's a big microprocessor inside that cell phone, and it really crank out the number, doing all the mathematical calculations, and it turned out a beautiful image as come from a good camera. So that is really the cutting edge research now. A lot of research are done on this. And it is a major industry there in the US. Okay. So let me just show you here these DSP appliances, right? The thing that you use at the home that based on DSPs. People in the US, and I'm sure in Vietnam, a lot of this. So like I should tell you about the cell phone, we talk about the digital cameras, digital television is coming in the US and the rest of the world, right? So the information just getting to you is not just the signal, the TV signal, but now it's a digital form. And a lot of the time, well, definitely would be compressed. So, you know, you can send maybe through the cable television 500 high definition TV channel. Right? So that requires very, very dedicated smart signal processing. A lot of other things, you know, you can use, people set up with their home and so on. So this thing is using daily life. This thing is boosting the economy in the West because of those kind of devices. Let me show you another example thing that maybe you don't see too often. But the thing, for example, let me show a quick example. Anyone know about the city? Okay, a few of you. Nowadays, for example, you know, someone in your family has some problem, you go to see a doctor, and they recommend to have a CT, right? What it means here is the doctor wants to see inside you, right? Let's say the doctor wants to see something inside my brain. One thing they count my brain, look inside. But the other thing is they can shoot some of these X-ray and they record them. And the big thing here is they need a big computer. Crank on those numbers and do some of those computations, and that is DSP. And it turn out to what is the image inside you, right? There's a major invention of the 20th century. Have the doctor. We ask all the doctor what is the major scientific improvement of, you know, for medicine in the 20th century. They talk about imaging because it allows doctor can see inside a patient, and you see that there is a major advancement. Several Nobel Prize was awarded to this kind of technology. On this day, it is my favorite example. I'm very fond of this because one of the major achievement, key fundamental contribution in this field is done by a mathematician in Vietnam. Anyone guess who? It's Dr. Quang Thuy. It's called tweak condition. Any algorithm want to be able to reconstruct an image have to satisfy a so-called tweak condition. And that is a mathematical algorithm, mathematical conditions, showing and listing out doctor routinely in the hospitals in the US. Okay, so it illustrated that what we need here, let me show you this. Okay, so we see here right now there's one single microphone and camera is recording it. Okay, and that is a traditional system in audio and video recording and playback like television. Right? The thing that in the US now people are pushing now is those devices getting cheaper and cheaper. In this room I can put not just one, but let's say 10 or 100 cameras recording from different angles. And based on that, we can put them together to a computer and I can use a very complicated DSP and can deliver something for you that you haven't been able to see before. And that big box here is what's going to be needed in the processing. So let me show you that little movie here. So all of this camera now, the device is getting cheaper and cheaper. We get a lot of those, and we use better DSP. Okay, everyone get that point? Okay. Best 20 engineering achievements in the last century, in the 20th century. So like, you know, the power grid, invention of automobile, airplane, and computer, internet, and so on. So all of these things that the one that really driving the economy, really increasing, put the people living standard, improving the living standard of the people in the world. And if you can imagine a lot of them require a lot of the power of the processing, right? And that will be a trend now. So what I want to deliver here, you can see this is, you know, the farmer, the people selling the thing in the market, in the future they can have access to those technology. They get it cheaper and cheaper, right? Those people are getting cheaper and cheaper. What us we have to do is just have to think smartly, invest our creativity into those little devices, and the boundary is endless, right? You just have to imagine what kind of facility you can do with this. So that is the kind of passionate message that we are the teaching team want to bring here. The DSP is very suitable tool to boost the economy and helping the developing country, right? Because it doesn't rely on the heavy equipment. We can think about that we use cheap devices, but use them smartly, using better, using it more efficiently by dividing those DSP. And you see that they based on simply better understanding of mathematics, physics, and computer science. Okay, these things are the things we believe that people you are here are very strong. Okay. So let me show you here, just give you a kind of sense, and then we take maybe a few minute break after half an hour. Where we are standing now as our country in terms of the world, in terms of developing. Okay. And I use this number from the World Bank a little bit. What here is use the so-called the purchasing power. So they look at this gross domestic product, but they work it out because, for example, $1 in Vietnam worth maybe a little bit more than $1 in US in terms of how much you can buy. And the country that is really leading the world now, the US, but China is catching up very quickly. Okay, and you see that this country here. Very familiar names, right? They play very well soccer as well, football. But you can see that, and Vietnam is ranked number 37. So, but you can see the number here are much more than as a country we would like to see, and in terms of per person are very small. So the message I want to deliver here, really, I love again, make it very passionate about this. Is in the future, an economy or country will have two choices. One, it would be the user of the technology. Right? The other one, the one that really driving those countries here, is the one that know how to create the technology. Need to know not just really turn the knob, but understand what inside that. And in dividing this course, we're very able that. We want to give you a very deep understanding, and I see that would potentially, we learn DSP with one goal is going to create a technology in terms of to help the people and help the economy. So that's the key message. And we want to look at that as the big pictures. Okay. And so people around here are the ones that are highly selected. And I can see people here would be the leader in that field. Right? The leader is the one that can know what the technology is going to be and want to create new technology. Okay. And that technology would lead the economy and lead our nation. Okay. So I summarize here what is DSPs and what is going to be involved. It's going to be a field that's going to leverage the background, the strong background that we have, namely mathematics, physics, and computer science. And it's going to link those strong foundations to the application. Right? We put together and we look at them in a smart way, and those applications are the ones we create new technology, helping the people and driving the economy. Okay. So let me stop here about 5 minutes. We can take a move around before we move to the blackboard. Okay. Here is, I'm going to start at the very basic level. Okay. So maybe some of you, I was just having a conversation here. Some of you may already see this material before. Okay. But some of you haven't seen it. But never mind. This is where the graduate level DSP course also starts. When I teach a graduate level course in DSP, in the University of Illinois, we teach exactly this. Start from here. Two reasons. I hope this talk would help you. One is help you to familiarize yourself with the terminology in English. Right? So it can help you to read the material. Maybe you see it before in Vietnamese, now it's time to see it in English. Second thing, as I said, each thing we can teach them a different level. And if you can teach as difficult as English. So I'm going to try at a very, very deep level. And the deepest level is when you will do the homework. Okay, that is where you can try to really test our understanding. Okay, so let me start. In DSP, okay, I'm going to use digital signal processing, DSP. It has only two characters. So the first one is signal. Okay. Can you see that in the back? Okay. Second character, you only need to know two things in DSP. Okay. First is signal, and the second is the systems. Okay. So we only need to know two things: signal and system. Now, signal is many more signal and many systems. In signal, roughly there's two types of signal. So we could have so-called okay, by the way, I would highly recommend you to take note. Okay, that's how I learn. When I sit in a lecture, I try to copy what the lecturer is writing and maybe note some more questions. Right? This is how I learn. Keep me stay awake. Okay, I hope you can help me too. Okay, the first thing is the continuous signal. And example for it is XT. So it is something like we have a count or a variable and we have a signal. Variable, right? So that is a continuous, sometimes it's known as an analog signal. Okay? That's something you probably already heard. And the second one is a discrete signal. And the discrete signal, so here T is a real number, okay, a continuous variable. And the second one is the discrete signal, and here N is an integer. Okay? So that is a discrete signal. And the discrete signal, sometimes we could have a signal like those form. So the signal here is N0, 1, 2, 3, and so on. So the signal is discretized. Okay, or it's sampled. Something we'll learn much more later. Okay, so there's two types of signal. Now, well, there could be a third type. Is after you have a discretize along this line, you may want to discretize along this line. And that called the quantization process. And that way you have a digital signal. Right? Because on a computer, everything is all digital. But I will try to mainly focus on this two type and ignore this quantization effect. And for that, in the US, people would call the discrete time signal and the digital signal at the same thing, even though it's not correctly. Okay, so far, okay, so we have two types of signal. Systems. System, loosely speaking, it's just something you can treat as a black box that have input in the signal and output is also a signal. And we have a system S beside that. Okay. And you have to think about that here is I take the whole signal, okay, whole signal input, I put through the systems and turn out to be another whole signal. Not just a set, not one number, not just one value, but a whole signal. Okay. signal can be just a function or a sequence of number. Okay. So maybe we take some example here. Let's take an example. Okay, so one signal I can see here is the impulse signal. Impulse signal. And it's a very important signal, very important signal. So you have a name. So we will put the signal delta n here. So I have a special letter denoting that signal, delta. Delta n here, the signal here, and we define it is equal to 1 when n equal to 0 and 0 else. Okay, so that's the impulse signal. We can plot them out. Plot them out as signal 0, 1, 2, so on. So here the n, we have minus 1 and so on. Everywhere else is 0 except there's one impulse. So that's why I call it impulse. Okay? So that's one. Now our systems, so let me give you an example of systems. Okay. For example, I have a system and I can write y of n is equal to, so I have a system here. So you think about it, I have an output here. I have an output here and I have to specify how can I compute this output based on my input. But also, what I have is a signal based on the previous output. Okay, so get an example here, maybe equal to, so I take this signal, maybe I start with two examples. So one signal is simply equal to summation n go from, so k go from 0 to n minus 1 of x n minus k. And then take the whole thing here, divide by n. Okay. Anyone have an idea what that system is? Taking what? Average, right? I'm taking the average. What I have here is I take the n sample from n minus 1 to n minus 1. I take them sum and I take average. Okay. So this thing you can see later on. For example, when people look at the stock index, right, and they can go up and down very widely. But simply you take the average of the wick, for example, n equals 7, you can plot them out much more smoothly. Okay, and we have to understand later on why the simple operation smooth out the signal. Okay, and I'll give a more example for that. So that one example. The second system here is maybe more complicated here. Yn equal to summation of k. I have ak here of yn minus k. K will go directly from 1 to n minus 1 plus summation l from 0 to n minus 1 x n minus l. We have missing here vm. Okay, so this system is every time I have to compute an output sample yn, I look at in the past my output and the input signal, and I take some of those combinations. Okay, so that's another example of a signal. And you see this thing here, I can easily write a computer program, right? People have you write some MATLAB or C programming before, right? You can program this thing easily. Okay? You see that? Okay. And we understand later on, this number, how can we construct those numbers so that it do something useful for us? My cell phone, those cell phone have something like this. Really have something like this. And by changing those numbers, we can do something very, very interesting. Okay. Okay, so now so these are two key concepts here. Signal systems. So let me going to now show more abstract type of systems. More abstract type of systems. I'm going to define now for you a class of systems. A class of systems that are quite general, okay, but it have a quite remarkable property. So I'm going to define here now a definition now of the so-called linear time invariant system. Systems S. So I have a system S, like this black box. But now I'm going to assume that it satisfies two properties. One is a linear system, two is a time invariant. So if, okay, let me satisfy two properties. One is a linear, okay, obviously linear time invariant. Linear, namely that if I have, okay, let me denote this form here. So I have this system here, and I can write them y of n is equal to s on x of n. Okay, so I take this signal, I put the whole system to it, and boom, you get it is out. Like the example I showed you. So now I have systems here. And going to be a linear systems in the sense of now if I have A1 have x1 n plus A2 x2 n. Okay. I take the output, I take these two signals here, now I take the linear combination of them, and then I put them through the systems. Then the output of that system can be written as really just simply a linear combination of the two output of those two original inputs. Okay, makes sense? So it's a little bit wordy, but in mathematical terms, simply written as I have an S. Remember, S now is a system. Right? Take not just one number, but give you one signal, give you another signal. So I take that x1 of n plus a 2s of x2 of n. Okay, so this is the linear property. A system that satisfies is a linear system. Okay, so that is satisfied for is a L. Okay, this has a whole term called LTR. The second property you have to satisfy is the time invariant. Time invariant simply put, I have a signal, right? So here I go through the systems, I have output here. Okay, right? Now I take my input, I delay them by some time. I put through the system, the output simply delayed. Okay, so that is called time invariant. So simply put, is I take S of the signal x n minus n naught here. So n naught here is a fixed, okay, it's a fixed number. Then our output here is simply we have trouble here. Let us assume that I have y n here. Okay. Then then that's simply just give me 1 of n minus n1. Okay? So let's describe what? If, then, okay. So a system, let me repeat, a system S satisfy these two properties is called a linear time invariant system. So called LTI. Okay? So let's have a play with that. Now, it turned out that two things. Remarkably, many systems around us can be modeled or can be assumed as an LTI system. Second, they have some very remarkable property which I'm going to talk about now. So you might have a system here, for example. Know why you think about this system. It's very complicated. I have a system here. How can I describe the system to a computer? Right? Can you think about how can you describe systems to a computer? Right? I have to build a system, right? And I have to instruct the computer to mimic a system to it. How can I describe them to the computer? Any suggestions? Input response, right? Okay, so you're one step ahead of me. But you see the problems here, right? If I have a system, that means just put in the input, I got something out, right? Not a black box. Put something in, something come out. And to describe that, you have to describe all different reaction to all different inputs. Right? You need a transfer function. You need something to describe the system. So it turned out to be a very complicated generally to describe the system. Right? But very remarkable if I have a system. So I'm going to state a theorem right now. So we have a theorem here. Let me state a theorem. So let S be an LTI system. Okay. I have here an LTI system. And as something that's suggested, the unit power response, or N here, is equal to the output of that system S based on the signal I used before, the unit pulse response, the impulse. So I put that signal in, and I get something out. Okay, and this thing here equals the impulse response. The response of the system to an impulse. Okay, obviously. So very simple, right? I have many different possible signals. I have to describe all possible outputs. But now I just need to focus on one particular output, this one. And if I have that, if I can get hooked to that thing, then the Yn, now I can be able to describe the output of any other system, so any other signal. Then Yn, by definitions, then Yn here is by definition is output of the system to that. Then what would be? What would be? There's a convolution there, right? There's a convolution there. The Sn here is to be the convolutions of x. So I have an x curve here, and I have an h of n minus k. The curve is a line here, and that is a convolution. Okay. So we need to write that is X compound with H in N. Okay, so let me repeat this theorem, and we will going to prove it. The theorem here states that S had to be an LTI, right? First had to be LTI, and LTI before any sense. If it's an LTI, then all I have to do is recording H with the equal to one. Then having that, I now can describe the system because this operation here, you can see that I can instruct my computer, if I know those H, and any X I put in, I can compute out. Okay? Is that clear to everyone? Now this thing here is an extremely important statement. So imagine, right? So let me put you a real scenario now. Many people here use cell phone, right? So you use a cell phone, and I talk to someone. They're going to transmit through the radio link, right? And to the base station, and then transmit wirelessly. Now, and it is known that when I send that information wirelessly, they have a lot of trouble, right? You get to the one bounce back. You get the ceiling, so there's a lot of difficulty within that, right? And very, very different varieties, I mean. And then I have a signal at the other end. So you can see that I send a signal, I say something, to go through the channel, this channel, and something comes out here. Now this channel here is something I cannot know beforehand. I cannot know beforehand. It's very hard to model, right? I cannot really model my cell phone of all different setting, combinations, and so on. Very hard. So you see that you have a black box. And then I really need to know this thing because I put something in, something come out here, very corrupted, and I need to know what the system has done to my original input so that I can undo the operation. Right? I need to know the system. You understand, right? Without the problem. So very hard. And one way to do that is I have to tell what I send, and I can tell to describe the system, I have to tell the input and the output. But that really defeats my purpose, right? Because I only want you to see this. I want you to know what this is. Right? Can you see that? So now the communication channel. One thing people can do very simple is based on this theorem. Before you send any information, you want to test the system, right? You simply send impulse. You put them in and let the other end record what's come out. Right? And after the record what come out, for that one single input, you say, aha, now I know everything about the systems. Right? And I know everything, I know what is doing to my signal. And based on that, I can undo the operation. Right? We talk more about that. Now, given y, I can know what is the original thing. So that's something you can see, right? What is the problem with that? What is the problem? Yes? The sum here, k here is just, let's say the integer from minus infinity to plus infinity. So the sum is k. Okay. Take all the k. It's a good question. Yes, we have to show exactly what is going on there. But the thing we want to capture here is, believe us here now. If I know x, I know h. I can compute y on every end. Right? A simple summation. So the example I just tell you earlier on about the systems. What is wrong with that? Or what is missing there? Excellent, very good, yes. The suggestion here is the summation here is good in the mathematical term, right? But you have infinite sum here. Our computer cannot wait forever, right? You cannot wait a friend there, let's wait, right? Let him just, compute this. You have a certain delays that you can tolerate, right? So cause is way and nearly fixed is maybe you can truncate. If this thing going to decay here, going to be small very quickly, then it can ignore. Okay. So yes, we'll talk more and what truncation have to have impact in the overall system. Very good. What other things? In my example, this communication channel, what other things that we have to be aware? I want you to take as an engineer or designer the stable of the systems, right? I put this thing in, maybe something come out here is very large, and it might break the system. Very good. What else?
Casualty.
Casualty.
The casualty.
The casualty, yeah, okay, yes, the casualty, yes, something very important, yes. So maybe I want to compute this thing, but I cannot do something X in the future. Yeah, that's exactly right. Yeah, I want the real-time system. What else?
I think it is very important when we have the linear time invariant system, because in my opinion, the signal, every signal can be a summation of the equal signals.
Yes.
So if we don't have the first property, we can use the summation of equals. So I think the most important is linear
time invariant. Okay. Yes. Yeah. Yes. That's exactly the thing I'm looking for. The example I tell you early on that I can use this trick. That means I have an unknown channel. I want to find out about that channel, and I tell you the trick that all you have to do is just ask the other end, send an impulse, record the output, know everything about the signal. Well, that thing only have to remember the theorem I said. It has to be an LTI system. The system you have to be assumed in the LTI, right? And that means you have this tool. And as someone just suggests, it is quite a strong condition. But the communication channel, let's say, what they do is they assume that, let's say, even in this room, the system quite the same. So it is going to be, the linear time invariant system for that particular time. And maybe when you run to the other end, for example, you're going to send out the impulse, and you're going to get another system. So the communication channel, regularly you have to update and try to find out what is the system, the new system at each time. Okay. Any other questions? Okay, so we have that. So now I want to also stress a point. It is very important for us to understand the theorem and proof. Right? As I tell you, I'm going to teach us in the graded level of signal processing. So we don't just know the statement, the result, but we want to know what's the reason behind. And we have to rigorously prove it. You have a wire systems, you have to prove that the system works all the time, right? And some mathematical term you have to prove the statement. So that is important, and people out there design those systems, they very understand the thing very deeply in that level. Okay. And in the homework exercise, you will have a chance to redo those steps. Okay. So I'm going to prove this theorem here. And to me, it's a very fundamental theorem. It's not just in signal processing, but in general linear systems theory. Okay. And in the process of proving these theorems, we will touch upon the following concept of signal decompositions. Right? Signal decompositions. But let me ask first, who has seen this theorem before? Raise your hand. Okay, a few of them. Who has seen the prove this theorem before? One. Who can prove this theorem? Okay. So it's good to go through the proof, right? Okay. So you have to have a proof of this theorem, and that's why I would say we want to understand the thing deeply, and we keep ourselves always questions where this result comes from, right? One of the things that key inside my web research is I never stop questioning, right? Always ask questions, and that is what when you see this thing. So okay, I have to do this proof. Okay. First, let me notice this whole thing. Notice I have a signal X. xn is a synchronous sample like this. And I have n here. So this is a signal, right? Oh, by the way, I use a notation n with the square around it, denoting that it is a discrete signal. The n here is an integer. Okay, so it is a sequence here, so here's a value of n, 0, 1, 2, and each n here I have a value. So signal is the whole sequence. Okay? So I have that signal, and at first very hard to deal with the signal, like the whole sequence. And here we're going to use a strategy that the Romans used 2,000 years ago when they want to conquer the world. What they want to do is divide and conquer. Right? I break the signal into small pieces and I deal with each piece separately. Right? You have big problems. The way to solve it is break them into small tasks and you deal with them separately. So that is one techniques that an engineer or a DSP engineer have to master. Okay, so I have a signal here and I want to break them into small pieces. Small pieces. And one way to do that is maybe I have a signal, I can think about it the simplest summation of a signal that first only have this. And a signal only have that. A signal only have this. And so on. Right? So if I just add them all together, I have the original signal. Can you see that? So I can notice that xn here is equal to summations. Write the more complicated way is I write them in the xk delta of n minus k. Okay, so the delta n minus k here, if you think about that, delta of n is a signal here. N minus k, you just delay it by k. And you have one here. And you take that and you weigh them like hk. Okay? So this thing you can verify, right? But it's really stable when you break the signal into small pieces. Now that value is, everyone agree with this, right? Now I want to write them in my special notation here. I want to treat this equation a little bit differently. Either here is a signal, and I want to put them in the square bracket. And this simple summation here, I put this square bracket here is a signal, and this is a scale, a number. Okay. Everyone understand the difference between a number and a signal now, right? A signal is like a function, a sequence. So you have a value at every instant of time, or instant of or every time. A number is just one number. Okay. So here I have a signal here. It is representing its n here, but for every n. And this equation here. So now it is one simple signal weighted by this. Okay, so now you see more clearly the thing I can break this signal into summaries of those small signals. Alright, makes sense or what? So I have it down now. So now if I apply the first linear property, the L here is I allow it to take S, apply on xn, and the linear property tell me that simply equal to the summation of xk. So these are just weight. Those are just weight. Okay, those weight here. And I put the S and I see what is output of delta. Okay, so take that S and delta n minus k. Alright, with it, right? That is the linear property put in place. Now, I'm going to use a TI now. The TI property tell me now. If I have only n here, what would that be? Hn by my definitions. Now I have this property Hn minus k because the system is a time invariant. So using the time invariant now, I can replace this thing now by Hn minus k. That's it. That's what I get my theorem, right? Exactly that formula showing there. So a very simple two-line proof, but it carries the very important concept I want to reinforce later, is I prove the signal based on breaking the signal into small manageable pieces. Okay? And understand where is a value and where is a signal. Okay? So if you haven't catch up this, tonight exercise, try to repeat it. Very important theory. Where the statement and how to prove it. Okay. And as I tell you, it has extremely important impact in signal processing and many other areas, right? For example, one of the areas very hot now, I know, is the bioengineering, right? So people study a particular cell, a neuron cell, for example. Right? So that cell we have modeled because the cell, including some impulse, we get send some signal. Right? Our whole body is just a sequential system. Right? We have something, let's say the temperature, the cell reacts something, and it transmits something, and it send the neural signal all the way back to the brain. Right? And people try to understand that very complicated systems. And what they do is they break into small pieces, and for 8 systems. One way to understand the system is they send some impulse, something like delta here. They record the output, and then they can know exactly what the system is doing. Try to model the system. People want to understand what is communication from here to Mars, for example. And this channel is very hard. All you have to do is send an impulse and let the other side record it, and then you know what is the communication channel for the whole system. Right? So those are important. So in that particular proof, I want to carry on now to another concept of breaking things into small pieces. Here I'm going to show you this convolution and it deserves a name and you see later. So this operation is happening all the time, and this thing here now I can write on this H convoluted H, and I have N. So you know that H is a whole signal, H is another signal. I convert two things, right? Using this formula, I got something for every instant of time. Okay. So, the signal I have so far, I think about them as a function or a sequence of numbers. Now, another way to think about the signal now, rather modern concept, which will be used later on, is now going to think about a signal. I'm going to associate it with a vector, right? I'm going to associate a signal with a vector. So for example, I have a simple signal now. Maybe we have 2 samples, 0 and 1. And this signal here I have a sample. So here's an N, maybe here is 3, and here is 2 here, for example. And I'm going to think about that signal now, not just any signal, but I think about it is a vector. Right? A vector now is, maybe you learn about a vector is, you have 2 coordinate systems, right? But I have 2 samples. And the first one is a 3, and the second one is a 2. And the signal now is just a single vector. Okay, I represent the whole signal now as a single vector. Okay. And the vector, you learn about the vector, can have a finite dimension. Well, we have 2 dimensions, something in the plane, but it can be many more, right? High dimensional, or it can have infinite dimension. Okay, so something quite abstract, something that allows to move quite far. So a signal is a vector. I can associate them now with the concept of vector space. And vector space signal processing is a quite modern view of signal processing out there. So I have a vector space. I have a vector space here. And okay, here is specified mathematical definition. So let me define the vector space. Okay. So a vector space V here, it has all the small vector V, and it's going to be, I'm not going to define the whole detail, but basically you have two things you can keep in mind. I have vectors, I have a lot of vectors, and I can define, the vector by itself is rather boring, right? You cannot do anything with this, like you have signals sitting around. But now I can define two things I can do with my vector or signal. One, I can add two vectors. Right? I can take a signal and add another signal. And two, I can take a vector and I can scale it up. Right? Well, I'm speaking right now and I can scale it out. Okay, just raise my board. So there's two operations I can do. So I have V1 plus V2 and I can have something like alpha and V. Okay, so this gives me something as a signal or vector, this gives me something as a vector. Okay, so vector space, loosely speaking, is allowed to do those two operations. This thing here, you know that is equal to scalar. Okay, and either a real number or complex number, or particular area. And this thing here, and all of this here is a vector. Okay, so that's simple things. Okay, still with me? So I'm going to treat now a signal now as a vector, and I easily define these two operations, a very abstract form. Now these two things allow me to do this simple two operation now, allow me to do a more complicated thing now, is so-called a linear combination. Linear combination is let's say I have a collection of signal. I have a collection of signal V1, V2, Vn here for example. And I can take different linear combinations of them. Right? I take, let's say, alpha 1 of this, alpha 2 of this, alpha n of this, and I add them together. And I have also a different signal, right? So this thing is very to get out from a vector space. Okay, and the linear combinations here allow me to do something like, anyone understand about the concept like linear independence? We have heard about linear independence. What will tell me about this? Okay, so I think everyone understand that. Okay. So for that simple, so those concepts, so this is very familiar, right? Okay. But I want to put them in the context of signal processing. So the linear combination here allows us to now, for example, the thing I simply do before, I have the vector here. Any vector here can be represented by a linear combination of these two small signals. Right? Something we see before. And that thing is nothing but, if I have a signal, and I turn the signal to the vector, what is the notation for this signal? This signal, what does it look like? It looks like something like this. What this signal will look like? Zero is samples, right? It is simple. 0 here and 1 here. Sorry. 1 here and 0 here. Right? So that is this signal here. That is the signal. How about this one here? This signal here is the signal when it enters this 0, 1 and here 1 here. Okay, so these two vectors are the two basic vectors, right? Two small pieces. And this just simply is delta n, and these are simply delta n minus 1. Okay, so the operation I run here just simply say that I have a vector space, and these are the bases. Very simple basis. Okay, and I can break my signal. I can write this signal here as a linear combinations of small pieces here. Okay, so you see that. And now after the break, I will show you a very rather powerful tool that, well, you know the vectors here. These are two coordinate systems, right? Not the only one. I can expand them by two very coordinate systems like this. I can use a different coordinate system, right? And one of them, very important, is the one using the Fourier transform. The Fourier transform is nothing but I can write a signal as a linear combination of a different basic signal, right? This signal is, boom, quiet, and then quiet, boom. Fourier is something like right? Different frequency. So I can break the signal into different small pieces, right? And in my experience, it's much more easy to think about Fourier transform and later on the Wavy transform as well in terms of the vector space decompositions. Okay, so the time to revise and think about the linear algebra, right? That's so good thing. And we have included in the textbook a review section of linear algebra, right? I believe you've seen that, both of you already seen that, but now just maybe translate that into English and then just revise that. Okay? But it is a modern view of looking at the signal processing using abstract linear algebra. Okay. Okay, so time to take a break now. I think coffee is ready and we'll be back here in 15 minutes in signal processing. The so-called vector space framework. Okay, so let me repeat here. We have a vector space. Vector space. And let me call the vector space V, where a vector is associated with a signal. Okay, each vector is one signal, and they have a whole space of signal. And we can do two things I described earlier on. One is we could add two things. So vector is a signal, and we can do two things. One is we can add, and two is V1 plus V2, and two is we can scalar multiplication. And I can take a number and I can scale it with a signal. So these two operations. Now later we can do something, another little bit more complicated operations. Quite interesting. Another abstract operation I can do now. I'm going to introduce a third operation. And a third thing here, which going to extend my vector space a little bit, is the so-called inner product. An inner product. Inner product. An inner product now is, I'm going to define the, I don't know what notation you use, but the notation that the textbook in the US use often is you take a vector U and inner product with a vector V. So take two vectors and give you another number. Okay. So that is the inner product. And if this number here can be either, this number can give you a number, either real numbers if you have defined this thing here is a real, or a complex number if this thing here is a complex. Okay. So let me make it. So this is the inner product here. And let me give right away now an example of that. So an example, for example, if I have thing in the vector space Rn. Okay, so I have an n-dimensional Euclidean vector space. Right? Each signal have n samples. Okay, and n real number. So I have two signals, and I want to take an inner product between these two signals. So the signal U times V here, this thing here can be defined in the summations n go from 1 to n. No, I have a dimension here, so we take the index I go from 1 to n of U I V I. Okay. So I take two vectors and I take the inner product. Okay? So that's very familiar inner products, right? The cross products, the dot product sometimes we go through. Okay? So that inner product. And this summation here, if I start to use them here, a vector now, I can write the vector now, a signal vector now. Typically, we write the column vector, a column vector. So if take a column vector, you have single x, and if the column vectors, so it would be equal to x1, x2, to xn. Okay. So an n-dimensional Euclidean vector space having all of those vectors. I have n entities. Okay. And to define an inner product, simply take this summation and take the sum, and so I take the product and I take the sum. Okay. And I can write the more compact form. Is simply I can take one vector with the transpose and multiply with another vector. Okay, so I can write this now here is U transpose times V. Alright, is that something okay with you? I take the vector U transpose and multiply with this. So what you use, you can see a little bit confusing here. I have U here is the whole vector, and V here is a vector, and I can write it this way. Okay. So that is in a real form. Now sometimes the signal we use, especially useful for the Fourier transform, we would use complex number. Right? Complex number, then the inner product and the complex number defined slightly different, and I take the same thing, summation I from 1 to n U I V I, but now I have to take the complex conjugate of one thing. And in this notation, let me take the complex conjugate the first time. You have to define them a little bit carefully, just follow one notation. Okay, so take complex conjugate in one, and then that allows me to write it. Now U is I take U and I transpose it, but then I take the remission. I take the conjugate of each number. Everyone understand the complex conjugate? What is complex conjugate in Vietnamese? Linear foot. Okay, linear foot. Okay. And the name of this is the transpose. And this one here is the H here stands for the remission. Remission. So have X here, and somehow we can define X transpose. So X transpose is equal to the vector here, x1 complex conjugate, xn complex conjugate. So you see that activities, right? And it is, if you say them in English, we would call X commission. That operation. Right, so there is a two specific example of the two vector space that I have an inner product. We can have other one, right? Other vector space. more general, I can define more general inner product. So we have to understand now, what is inner product telling us? Right? What is the inner product? The inner product allows to do something. Maybe we start with the simple two-dimensional Euclideans. So if I have two inner products, vector space, I take an example here. I take an inner product of we want to have those simple vector. I'm going to have some special signal. Before we have the delta n, but now in the inner product vector space, I'm going to use a vector e. I have a trouble now because we are okay. So the vector now you know by the whole thing here. So the E here, let's say I have E on here, E is the vector space, the vector, especially is have 0, 0 everywhere and have 1 at the I. Okay, so that is like the delta n minus I signal. Okay, this is the basic signal. So I have this so that that is a basic vector. And what happened with this signal? If I take an inner product, so for example I take this E1 here and have a signal x here. So if I take x and inner product with EI here, what does it give you? It gives me xi, right? It gives me the xi now. It just gives me the component I of the vector x. Okay. So that gives me something like, okay, in taking that inner product, and we see later on something quite important happen for not just the simple signal, but any other transform can be interpreted as well. Okay, so that's coming. And the bigger the xi, small xi here, that means the more strong component EI in this xi, right? Small signal. For example, so the inner product is quite remarkable properties. Another example here, and maybe I can let you to think about this. You can show easily. If I have two general vector here, let me call them x and y, and I know that the angle between x and y as alpha. Then the inner product, this thing you blow on this elementary geometry course, we take x and y here, these two, normally it would be equal to the magnitude of this, multiplied with the magnitude of this, multiplied with the cosine of this angle. Right? That's something you see before. You can show that easily. Okay. So the magnitude of this is x, and the magnitude of this is y, and times the cost of alpha. So another principle. I'm not going to really show, this is just recording because I trust I've seen this thing before. Okay? Now what is the magnitude of this? The magnitude of this thing here is if I take x, I define this by definition. You can see that if I take x and I inner product with x, what do I have? Let's take the real thing for simple. Take x, inner product with x, what I do is the summation of xi squared. Right? And if I take the square root of that, that gives you the length, right? The magnitude of the signal. So this thing here is the definition of how to get this thing. And that thing actually can be defined for any inner product vector space. Okay, so in terms of signal processing, I want to now relate it back to signal processing. These operations of taking this and multiply with this give us some measurement measurement of how similar these two signals is. Right? Because if x and y are very similar, then this angle here are very small. And if it's small, that means the cost will be very large. So two signals are very similar, we're going to put up the inner product. And what is the worst case? When this inner product will be very small, in magnitude terms. Two things are orthogonal, right? Two things are orthogonal. If the two things are orthogonal, then the inner product equals to 0. Okay. So another thing here, in the definition here, is we have x orthogonal with y if inner product x and y equals to 0. Okay. It makes sense? Alright. So these are simple things, but now let me see how can we look at a very complicated vector space and look at how to decompose the signal. Alright, so for example now I imagined, or you imagine that we have a signal, a simple signal vector x. I'm going to back to the operation I had before. Take a signal, break them into small pieces, these unit poles and these delay poles. And as I said earlier, I take the signal x here, and it has a samples so maybe sometimes we start with 0, it's 1, it's n minus 1. Okay, so this signal here easily can be broken. This thing is not hard to see. And 1, 0, 0, 0, and what I put the scale here? x0. Okay, plus x1. 0, 1, 0. So on here, and plus x n minus 1 of 1, 0, 0, 0. So this is very simple decompositions of a vector into a linear combination of those basic signals. Okay, so those basic signals I can call them as E0, E1, En minus 1. Those vectors. Or if you recognize it, if I write the signal in the sequence number, and you think about that it is axis n in this end, and here's the origin, right? And these are sample, here's another origin here, here's the origin here. Then this is just a signal I can think about it, right? And 1 here, 0 everywhere. So what is that signal? The delta n, right? The delta n you see. So this is just delta n. What about this? Delta n minus 1, and so on. Okay, so simply I take a signal and I write them as a linear combination of different basis components. Okay, put them in more abstract form. I'm assuming now more general, right? So this is one basis, but now what we think about now is I have suppose that instead of having n simple signal now, I have a V0, V1, Vn minus 1. Suppose that I have this collection. For simplicity, sometimes I draw this vector. But okay, so I have this thing here is the basic. The basic, so anyone remember what the basic is? What is the basics? Okay, so something that you write this form. Mathematically, it has to be satisfied two things, right? One, it has to be linearly independent, right? And two, right, any signal can be written as a linear combination. Okay, very good. So that, and I have this as the basics, and others I can just describe, right? So I can write now any signal x equal to alpha 0 V0 plus alpha n minus 1 Vn minus 1. Right? I can write this form. this form, I want you to think about this summation. Fundamentally very important now is now what happens if I have a signal x. I have a basis. Right? This basis, I just give you a hint ahead. It can be either a Fourier basis or Wavelet basis or any other basis that we can construct later on. So I have a signal, and very important we want to know what is the component of those bases. Right? I have a signal and I want to represent the Fourier basis, and I want to know how much percentage the signal is, like 5 megahertz, 10 megahertz, and so on, right? And I can have a signal. When we listen to something, what our ear is doing is really decompose the signal into different frequencies, right? Because different words have a different frequency component. And what it does is really do this kind of computation. Okay, so let's see how can we do it by a computer in a mathematical algorithm. Right, so the question here is, how can I find out an alpha, those alpha, given the signals? Right? One way to see this simply is by, and I want you to think about this form, and maybe useful later on for the homework exercises. We can write this now by putting all of those b, so I have b0, bn minus 1. So this is a vector, and as I said, a vector is a column vector. So I stack them all together here into a matrix. Right? If I have a basis, I have this matrix. No problems. And the alpha that I have, I can put them now in the alpha 0 to alpha n minus 1. So everyone see that this matrix multiply this column vector give you exactly this. Right? Agree? Right? Everyone agree? Raise your hand if you disagree. Okay. So that's the right? And I have this thing here now, and now I can do now simply, maybe I can put a more abstract form. I can write x is simply equal to that thing is matrix B times x, so some alpha that is. Okay? So now to be able to find alpha, very simple. I could simply do the operations. I could simply do the inverse. Right? I could simply do the inverse. So to get out alpha, so get rid of the questions, I have a signal, I have a basis, and I want to find the component, the expansion of that signal in that basis. Well, then simply we can write out alpha equal to b minus 1 times x. Okay? Simply. So we can write this. Now, finding this b minus 1 sometimes can be troublesome. That can be a little bit difficult. But now we let's say, now special case. I'm going to give you an easy case now, but very important. Suppose that b0 bn minus 1 is an amplified new terms now, is an orthonormal basis. So it's not just any basis, but it's an orthonormal basis. It's the basis where the components are orthonormal to each other, right? That is, I take bi, let's say bk, hand with bj, bl here for example. I take these two. This two thing here is equal to 1 if k equal to L, and as we said, 0 else. Right? So the vectors are mutually orthogonal to each other, and when k equal to L, I normalize them to have really norm. Okay? So that's a very nice basis. So what is nice about this basis? if I have this, so now if I write this thing here, and you know that this thing here is nothing but a technique. I'm going to do the real vector space now for simplicity. It's just really the transpose can be equal to this, right? Because that's our inner product. And now, it's not how to imagine. What I want to do now is I cut the matrix B I have earlier on. So B all of this vector. Okay. And now I write this B transpose. I take the B transpose. So transpose is I take all of this vector and I turn them to be a row vector. Okay. So if I have an orthonormal basis satisfied with this, what B transpose can be equal to? It is equal to 0 anyway, right? So I have a matrix. A matrix, have a matrix, give me a matrix. Everywhere else, they have a 0. Except along the diagonal when the same vector hits itself. Right? And have a 1. So this thing here, you have a name, it's called identity matrix. Right? This is matrix I. And now you have something multiplied with something. Give me an identity matrix. What this have to be? This is simply a big minus 1. Right? So simply now, so from there now, what we have is a B just minus 1 here is equal to B transpose. So getting the inverse B here is very simple, simply transpose matrix. So that is an extremely nice property about an orthonormal basis. Now if I take that, so now I have this thing now, and now so what happens now is this thing. Okay, I'm going to have that. Then now is equal to B transpose X equal to B transpose X. Maybe I have to do. This is for general, right? Mixes. This is for general here now. So in this case, only in this case. I have alpha equal to simply B transpose X. And B transpose is just simply taking this, and with this. So, or if I have to find all the X, those alpha components, all I have to do here now is I take that row vector multiplied with X. And what it is? This is inner product. Extremely simple. The inner product now is taking Bi times X. Okay? Very simple. And this is any orthonormal basis satisfies. And later on we look at the Fourier basis, weighted basis, we look at this very simple case. Alright? And remember the early example. This basic here is an orthonormal basis, right? Easy to verify. Taking off from any two guys, they are orthonormal. So we showed the early example, right? Take those terms, simply taking this, inner product with that vector. But this is not a matrix, it's code for general any orthonormal basis. Okay? So let me now define an orthonormal basis of extremely important in signal processing. So that's clear now? Okay. So we're going to define now an orthonormal basis that we would use often in signal processing. So now it is suppose now, another example now, I'm going to look inside the vector space N in Cn now. And I look into this basis. I'm going to call them now is I'm going to define them. Maybe let me do it in a different way. No, I'm going to do them in the upside down way. So let me go back to the thing that you probably always see the discrete Fourier transform. So this thing here, I'm going to look at the basis, is the one that maybe you are quite familiar with, is the basics I have now, the F0, F1 and so on. So all of these bases, they are, so the first one here is just simply 1, 1, 1. So all 1. The second one, it is 1 EJ 2 pi over, so I have Cn here, so I have to use a little bit of the capital N here. We'll use a capital N here. And I'm going to have here 2 pi over N, and then I have Ej of 2 pi over N times with 2. So you see the patterns, right? So that to e to the j of 2 pi over n of n minus 1. Okay. So maybe more general here, if I have as vector f here, what it is? Well, just simply this. The k component here, so the n component here, it is simply e j 2 pi over n of k times n. Okay, can you see the pattern? Right? Another pattern. We are engineers here, right? We want to use a notation that the j, we know this is the imaginary number, right? Minus 1 here. So that is our notation. Okay, and I can leave that as an exercise for you to show that this is an orthogonal basis. And you can normalize them, then you have an orthonormal basis. Okay, so I have a basis there. And if I have a basis, then now, what can I do? Well, I can expand this basis. I can take any signal x, and I can write them is equal to summation. Maybe let me go a little bit careful by putting this, let me try to use 1 over square root of n. How about that? 1 over square root of n. It's easy to show that the norm of this signal is about square root of n. Right? So divide by 1 over square root of n, I got a unit norm. So if I take that now, so that's the basis now. Then any vector here, x can be summation capital K here, K go from 0 to n minus 1 of this f, the basic vector x k. Okay, so that's very simple basic expansion of this. And if I can write down now this thing here, and if I write this form here now, and this xk here now, because we can show this thing here as an orthonormal basis, then xk here is simply equal to the inner product of fk times with x. Right? So this number here is the inner product of this. Okay. So that is a very general abstract framework, right? But now let me blow them up here. If I have this, that means I have a vector. The vector is linear combination of those basic terms. So that means I take this particular thing here, just equal to that, multiply with that term, then multiply with that term, and so on. Right? And with that means I can write x n is equal simply summation in k, and I have 1 over square root of n outside, and I have inside here I have xk, and I have this thing here, the component of that is just e j 2 pi over n k n. Right? Anyone recognize this? It is a discrete Fourier transform forward. Right? And this part here, to find it, is just simply, this curve here is, if I take this inner product right now, it's just 1 over square root of n, and summation in corridor from 0 to n minus 1. And I have here the derivative x n. But now that I can incorporate conjugate with this, so that's why I see that sometimes we learn one have to be that and the other one is minus, so minus j 2 pi over n by n. Okay. So the thing we want to put in perspective now, right? The discrete Fourier transform, okay, so this is nothing but, okay, maybe when you learn that you have 1 over n, one and no the other one, right? So let's put this square root and here to make the thing easier to deal with. Okay, so this thing here is very important. Used all the time. Is called the discrete Fourier transform. Okay, this is Fourier transform, and it is so important that we have a name for it, DFT. Okay. And you might see the formula before. You see this formula before. What I really want you to understand after just this part here is understand behind the formula. What it simply means is you take a signal and now you look at that signal with a different basis. Right? The basis is not just those components, but the basis are those components. And the basic of those components, for example, the first one is just a constant signal. This one here maybe have some frequency, and it's getting higher and higher frequency. Right? So that is a key part here. And the Fourier coefficient that what we have here, what it's giving us here is how much of that particular frequency is contained in our original signal. Right? So that is a frequency analysis. And just give you an indication of how important this thing here is. People have this, and you know this. Computing is very, very complicated. Right? Well, we take about n squared operations. Right? You have n here, and you take n of those by n squared. Take quite a lot of time. And of course, we know that there's a fast algorithm to do that. It's called the fast Fourier transform. Right? Which is much faster, and it discovered around 65, and that people now contribute that is above DSP. Because after that moment, we can all carry this operation very efficiently. Okay, but behind that here, conceptually, it's just simply decomposition. Okay, any questions on this? All right. So, I don't have any questions. You have to do something that really make you to ask questions. How about I'm going to give you an exercise in the class? I want you to think about this. Okay. I want to okay, so how can I'm going to do this following thing. I'm going to consider this basis. I'm going to move a little bit further down, but let's see. So these operations is really mapping n number to another n number here. And the inverse transform is mapping n number back to this one. Right? And in the line now it's just a relation operation. So how about we think about the following? It's still here, let's see. Let me define the Fourier define the Fourier transform, and then we link them back later. So this signal only have me if I have only n sample signal. But now, for generosity, I'm going to define a discrete time Fourier transform. And that is the DTFT. I'm going to define this now. I have a signal xn. And go for any real number. So I have a whole sequence of numbers here. And looking at this sequence here, so I take the same sequence xn and I weighted them with this complex exponential signal. And instead of restricting myself to only this thing, 2j 2 pi over nk, I'm going to consider the transformation is, look at this function x, but now it's still only one sample. I have a whole continuous function. And I define that my definition is equal to summations in n go from minus infinity to plus infinity of xn e minus j omega n. Who ever seen this formula before? No? That's a new formula. Okay. But can you see that? Okay. I might use a mixed notation. Sometimes I use xn here, xn, the same thing, right? And maybe we should do what we here. So this thing here, what happens is I take a sequence and I have another function. This thing is nothing but a generalization of this form. But now I allow the summation, go all the signals and allow this thing to have any other value here, not just 2 pi n over k over n. Okay. Tomorrow we'll look at more closely the limit, and I think today in the afternoon we have some exercise to see that. Now, I want to tie up with this, the early part of the lecture. I have this thing here, and I'm assuming that you know how to go back. I'm going back here, so that is the forward version of this. If I take this and I go back to the inverse versions, then I can take this xn here. If you want to take back, it's easy to show, but I will not show them today. I want to show you something else. You can easily take this thing here and you can find out what the sample is equal to by taking this 0 to 2 pi, so what happens is go from minus pi to pi of x omega e j omega and e omega. Okay, so you see that this operation is something more general than this, right? Before you have those k, those discrete sample, now I have because I have all omega I take individually. Okay. So we have these fab transformations, take the signal, go to discrete Fourier transform, and I can go back. And there's a whole story of connecting that. And I want to talk about this in the context of sampling later. But now, what is this thing here has a nice property? And so does all other Fourier transform. Now if I go back to the early systems, remember early on. If I have this now. Now if I let's say, very important now. Let S be an LDR system. Let S be an LDR system, right? The system that's linear and time invariant. We know before. Now, if I have an LDR system, what do you remember from the first lecture? What do I have? How can I describe the system? I use impulse response, right? I use impulse response. So let I have the system that have H and here is impulse response of the system. Okay. So on this formula, what I'm going to see now is I'm going to take each of these components as one basic signal. The signal that is Ej omega m. The signal Ej omega m. So that means the signal is at the eastern end, we have Ej omega m. Okay. If I take that signal as input, okay, then the output of these systems, to be more precise, maybe we can know a particular frequency. So I fix this omega naught. Okay, I fix that signal here, and I want to work out what would be the output. What would be the output of this? So I take that thing here and I take the output here. Then the Y. So the output of that particular systems, is, I can write them now, the output that Y and here, simply just taking this and converting this. Right? Taking this and converting this. And write that, so summation now, and I take in K, and I take the convolution in xk, and I call this thing here, so this is xn. Xn equal to this. Taking this convolution here, I have h of n minus k. Okay? So I'm taking that signal there, and my output of this signal, my output signal, simply now, I can write this now equal to summation. So I plug this guy inside. What is the easier way to show? Taking this, so the convolution maybe I can write, easy to show that I can swap these two things, right? If I change that, the convolution maybe I can write, it is hk and it is x n minus k. Maybe easier. Okay. And if I have this now, then I have summation in k of hk, and now I replace this xn minus k. So what is xn minus k now? It is Ej omega naught, and I have outside that replace n by n minus k. Right? N minus k. So I have a summation and sum in k, summation in k. So this omega n here doesn't, when you go inside, I can move them outside. So it's equal to EJ omega naught N, and inside I have a summation of K of HK EJ minus now omega naught K. Is it correct? So what is this thing here? What is this thing inside here? By definition, it looks like this thing here. Right? So now it is equal to EJ omega naught N and then H of omega naught. Okay. Aha. So now you recognize the following. This omega naught is something I fixed. I fixed this. I fix this thing here and have a signal of that particular frequency omega naught. I pass it through the systems. I get out something like this signal with that particular frequency. Only thing I change is this. This thing I now get scaled up. Right? Can you see that? Simple equation here. The bottom line here is something we can go here, this thing here. We can go to this eigen signal. Right? The concept like the eigenvector. Remember, like you have an eigenvector, go through a matrix, you got something scaled by the eigenvector. So this is an eigensignal. So this component here is an eigensignal of any LTI system. So take this signal. So now I go back to this formula. You have a signal, and because now the signal is infinitely long. So my summation now is 34 integral, loosely speaking. And I have all of this x omega, and tell me now for each particular omega, this is a one particular signal, and that's the weight, right? And you put all the weight here. So I have a signal, I can expand them to the Fourier basis, right? Different components. And I take those components, bring the divine contour, and break the signal into those components. And put the signal through the system. It's like putting each component through the system. Each component, when they go through the system, remains the same, right? Remain exactly the same, except it gets scaled by this number, right? So you can see that this h omega is very important because the bigger omega, the bigger h omega, telling me that that particular frequency when it passes through get amplified. The smaller h omega, that means that particular frequency go through get killed, get rejected. And that is really the concept of filtering, right? You let an LTI system filter out any particular frequency or get particular frequency go through. Right? So you see that really the viewpoint, taking the signal and break them into small pieces, really is the main thread of this lecture, right? And it's explained them by a Fourier transform. Okay, so I have a simple thing now. I want you to do in class, right? I can see that it's near the midday now, people get tired. But I want you to do a little quiz now. I want a simple exercise. You might have it before, but I want you to now maybe find someone, every table, we can do them together, right? Maybe try to do first. I want you to show the following proof for me, the following terms. The following term here is if I take the signal x and I take the hn here, and I got the output here is yn. This is an LTI system. Okay, that is the LTI system. And I want to prove that the statement here is prove that in the DTFT domain, I get y of omega equal to h of omega times h of omega. I want you to prove for me that statement. And I want you to maybe write a little note on the paper now, about 2 minutes, and then you can turn around and discuss with your friend next to you. Rằng là trong DSP có hai cái, một là signal, signal tín hiệu, hai là system. System là take the input a signal and turn out that input a signal. Và một trong những cái important system mà mình học ấy, là cái system gọi là LTI, Linear Time Invariant. Và cái LTI đấy nó có một cái theorem là cái convolution theorem, và có thể lúc có thể nhìn cái theorem ấy dưới rất là nhiều góc độ, là có thể là cái theorem đấy là có thể any LTI system ấy là mình có thể characterize nó, có thể biểu diễn nó qua cái impulse response. Cái response là cái output của cái system khi mà mình send an impulse, impulse. Okay, so that is a very important result. Cái thứ hai ấy là mình xem hôm nay ấy là cái concept of thinking, nhìn một cái signal như một cái vector trong một cái không gian vector. Và cái key mà mình xem ấy là các cái vector ấy, có thể là mình có thể scale một vector, tức là nhân một vector với một số thực, hoặc là mình sẽ add hai vector với nhau. Và cái điều quan trọng mỗi cái vector space ấy là cái basics, đúng không? Tức là dùng cái basics là cái hệ chuẩn đấy, thì mỗi cái vector có thể biểu diễn là bằng linear combination của những cái vector chuẩn đấy. Thế thì cái concept ấy, và cái vector space ấy nó rất là cái concept nó rất là chung, và nó có thể apply về cái chuẩn đơn giản là bằng 1 và 0 của tất cả các điểm khác, đúng không? Và mình xem đây là simple, hoặc là dùng cái chuẩn basic là Fourier basic, và mình xem cái DFT ấy là Fourier basic, đúng không? Và cái concept của cái DFT ấy, discrete Fourier transform ấy, có thể generalize lên thành the discrete time Fourier transform. Khi mà cái signal ấy là bây giờ không còn giới hạn là từ 0 đến n-1 nữa, mà có thể là toàn bộ là minus infinity to plus infinity, đúng không? Thì cái đấy là dùng cái DFT là define như vậy là tôi định nghĩa cái DFT là như này, và inverse của nó là như này, có thể dễ dàng chứng minh là cái này sẽ luôn được là inverse. Thì đấy là có thể để cái exercise. Và cái mà quan trọng ấy là cái DFT ấy nó cho phép mình xem ấy là any cái LTI system này là mỗi cái này là như một cái eigen signal, như là cái eigen vector ấy, là mình xem một cái signal là ej omega, cái ej omega này vào thì nó qua cái LTI system ấy nó tạo ra cái signal cũng là cái ej omega n, nhưng mà mình chưa được multiply một cái số một scale up. Và cái đấy là chính là cái concept là những cái basic component, cái Fourier basic, cái chuẩn của Fourier ấy là eigen signal của cái LTI system. So the Fourier transform với LTI nó đi với nhau rất là quan trọng. Và cái concept mình sẽ go forward later on ấy, là khi mình học ấy là mình bây giờ là mình thấy cái này là mình mới là analyze, mình mới try to study, understand, tức là hiểu cái system này. Sau đây là mình có thể làm sao mình có thể design được cái system này, mình có thể thiết kế, mình có thể xây dựng cái system này dựa vào những cái đòi hỏi của system của cá nhân. Phải làm một cái system cho hệ communication system chẳng hạn, thì nó có những cái đòi hỏi nào và mình phải xây dựng được cái system thế nào, là đấy là cái topic của ngày hôm sau. Và có một cái nữa là mình sẽ phải xem ấy, là cái signal này, cái signal mình có trong không gian bình thường là signal như lúc đầu mình nói là có hai loại signal, một cái là signal liên tục và signal tương tự, đúng không? Và một signal là signal rời rạc ở tín hiệu số. Thì cái process từ cái signal, từ tín hiệu tương tự đến tín hiệu rời rạc ấy, là cái phép sampling ấy là phép rất là quan trọng. Ngày mai mình sẽ xem lại. Thế bây giờ là PA sẽ có announcement trước khi chúng ta nghỉ.